It's going to
live streaming.
Yeah.
Okay.
It's going to come on the other side. Right?
Super.
So how do you make students access this live stream?
They just go to your name. Google your name on YouTube. Then you have the name, for example. This is the way it is.
Access this live stream.
They just go to your name. That is Google your name on YouTube. Then you have the name, for example. This is the way it is. You can mute yourself from there. So you come here, you come on YouTube, then you say, okay, Manyika, YouTube, Manyika Davy, live streams, right? Live streaming. Then immediately it will bring, these are my lectures. This is how we teach. For example, this was what I was teaching last week.
Okay.
Okay?
Okay.
So, this is what the student is.
This is multiplied by ax plus partial v
Very nice.
of multiply a, we cross it into b, then we cross it into c. That way, this is the same as writing this as.
For this lecture, particular lecture, they should come here live now.
Okay.
So they open that.
Now they can
Writing this as.
For this lecture, particular lecture, they should come here live now. So they open that.
now they can
Writing this as.
For this lecture, particular lecture, they should come here live now. So they open that.
now they can
Writing this as.
For this lecture, particular lecture, they should come here live now. So they open that.
now they can
Writing this as.
For this lecture, particular lecture, they should come here live now. So they open that.
now they can
Writing this as.
For this lecture, particular lecture, they should come here live now. So they open that.
now they can
Writing this as.
For this lecture, particular lecture, they should come here live now. So they open that.
now they can
Writing this as.
For this lecture, particular lecture, they should come here live now. So they open that.
now they can
Writing this as.
For this lecture, particular lecture, they should come here live now. So they open that.
Writing this as.
For this lecture, How is the sound? How is the sound? That's wrong. Oh, okay, I'm going to come up and need it in just spare time. Oh, okay, okay. Manyika. Okay, kuna Manyika kaifanya. Mafua yao nasi. Although the business is Mafua yao nasi. Although the business is Okay, you are able to get me now. The sound seems not to be too okay. Are you able to see the board clearly? Please confirm so that I can make adjustments as well before starting. Just confirm if you are able to see the board clearly, if you are able to see end to end. And you confirm that before I can make adjustments on the zooming of the camera. Just type yes if you are able to see the entire. Before I can make adjustments on the zooming of the camera. Just type yes if you are able to see the entire. Just type yes if you are able to see the entire. All right, let me just try to do some final adjustments, then I'll start teaching. All right, let me just try to do some final adjustments, then I'll start teaching. All right, let me just try to do some final adjustments, then I'll start teaching. Okay. All right, so we can start. If all looks okay, we can begin. I'm seeing some people are still saying that it is still noisy. Please confirm if it is still noisy. Okay, we can confirm that. I'm seeing some people are still saying that it is still noisy. Please. Is it still noisy? It is still noisy. Please confirm by typing. All right, so we shall begin where we started from. Sorry that we had to miss class in the morning. I was called for a meeting concerning the graduation ceremony that is coming up. Sorry that we had to miss class in the morning. I was called for. Nevertheless, we shall see how best we can move this afternoon. All right. Nevertheless, we shall see how best we can move this afternoon. All right. All right. Last week we had done one example, which was a derivation. I'm sure. Right. You recall very well. We're looking at one example, which was a derivation at the electric field intensity of a charged ring. And today we shall continue to look at another typical example in that light of a charged ring. And today we shall continue to look at another typical example in that light of a charged ring. And today we shall continue to look at another. Okay. So let's look at the second example, which is the electric field. So let's look at the second example. We are looking at the electric field intensity due to infinite line charge. Let's look at that second example. Please, if you are not able to see well, just kindly type when I start writing. If you are not able to see very well on the board, just make sure that you indicate. I'll be able to check the messages that are coming through from you. Alright, so we look at number 2 as an example, which is the electric field intensity. Number 2 as an example, which is this is due to an infinite this is line charge due to an infinite. Right. So we had looked at the first example and we have seen how we could actually do the derivation that we looked at last week. So what we are trying to look at, last week we were looking at just a ring which has been charged. So we have a ring like this, and remember very well, we had gotten a small piece here which we called the DL. And this DL, we actually had to do a plot, and we did the derivation all the way up to the end where we got the final expression. So we had put a point somewhere here which we called point P, and then we had to do some dimensional analysis to see when we are at point P the amount of charge that is exerted on point P due to a small area that we have cut, which is the L. And then from there now we also looked at if we have now found the DL, the charge at that point as a result of DL, what will be the charge that we will get as a result of the entire charge ring, which of course we had to integrate from 0 to 2 pi in order for us to get the whole effect. Now today we are looking at the electric field intensity. This is not due to a child ring like we looked at last week, but this is due to an infinite line. In other words, what we have is that we have, this is our line that we are talking about. Then we take this to be our origin. Then let this be our y-axis. And then we have that which is our z-axis. In other words, when we say the infinite, it means that this line is not ending. That is the implication. If we say finite, it means that we are able to quantify the length of this line that we have. So now, what we have is that we have that line, then we have created our origin here, which is, this becomes our x-axis, this is our z-axis, and then what we get, actually we can extend this, of course, to be our x-axis, so that our diagram looks a little bit complete. Remember what we had done with the ring. We had, sorry for that, we had a ring like this, and we had put this, our x, y, and z plane here. This is z, this is x, that is y. Then we had cut something like I was explaining where we were just starting. Remember that we had put a point here, point P, so that we get the charge that we are able to get from here, or the force. In other words, when we started and explained about it, that is due to a small element here. In the same manner, since the line is in this direction, it is in the z-axis, we shall pick a point, which we are calling point P, on the y-axis, so that we can try to determine how much charge we are able to get from this line that has been charged. Now, what we are trying to do is that, remember, we have to get a small part here, which we have to make to cut there, so that we see the effect of this small component which we've cut here on this point P. In other words, if we are standing at this point, then this is the distance that we have up to where this line is. Remember, this line is actually charged, an infinite line charge. Now, what we want is to first of all try to make a calculation for the small component. From there now we can, after we found the expression for the small component, we can easily now do the integration and find the component for the rest of the of the charge, the line charge. Do the integration and find the. Okay, having said that, now we have to make some few assumptions. So we are saying that we actually consider a line charge. In other words, this must not be looked at to be a wire or some sort. This is just a charge that has been arranged in a form of a line. That's why we are calling it a line charge. So we want to see its effect when we are sitting at point P, to see how much force we are going to get from this line charge in relation to the electric field intensity that we are actually trying to talk about. Now, we are saying that let P, so we are saying let P, which is this point here. Of course, this will have our theta there. So this is our point P. And then, of course, P is at 0, comma R, comma 0, where we are saying the distance from our origin to point P, we are calling it R. And then from there we have, at this point, we have this, which is in that direction, which is our small electric field. Then we have the one that comes down is what we are calling the dE from the z-axis, and then we have in this direction we have the dE from the y-axis. So we are saying that we consider, so that is the P. We will not waste time to talk about the P. I've already explained about it. So now we're saying we consider, so we consider a, that is just an element. I've already explained about it. So now we're saying an element length. So we consider a, which is this one here, just a small element here, which we are calling TL. That is the one that we are looking at. So we are saying TL, which is carrying. So this is actually carrying some charge. So this is, and this charge we shall call it dq. So we have this small element here, which is actually carrying the charge dq at this point. Now, what we want to achieve is, we want to do a calculation particularly for this, so that from there now we can integrate for the entire line of charge. Then you'll be able to get the final expression that we are looking for. Right. So that from there now we can integrate for the entire line of charge. Then you'll be able to get the final. Just excuse me some minute. Right. So that from there now we can integrate for the entire line of charge. Then you'll be able to get the final. Just excuse me some minute. Just excuse me some minute. Yeah, sorry for that disturbance. I was just attending to some people who were busy knocking. All right. Now, what we are saying is that we have got a small dl here, which has charge dq. So we want to see its effect on the point P, which we have actually selected. This point P, it's not fixed. You can either bring it here, you can put it there, or what, but we just chosen to bring it here so that you are able to see what we are doing. Now, what we are saying is that this is actually along. So we are saying that bring it here so that you are able to see what we are doing. Now, okay, so we are saying that it is actually along the z-axis, as it can be seen from the diagram. This dl is actually along the z-axis. So now, what we are saying is that this implies that dl must be equal to dz. In other words, if we pick small components here, like that, you cut them like that, means we are calling them dl. Since it is in the z-axis, we can say this is just the same as the z. So we can either use the L or we can use the z, because it is along the z-axis. So we are able to cut those small pieces. So what does that tell us? This tells us that the line charge density now is equal to dq over dl, which is the same as dq over dz. So this must be taken care of, and you have to note that. So we are saying the line charge density, which is defined as the quotient of the charge over the length, is the same as the charge divided by the z. Where the L, we have said it is the same as the z in that way. Now, what we have, from there now we have to continue with our derivation. You can put this in a square, So that's very important. So what does this tell us? If we try to write this, what we get is that this is the Q, which is equal to the charge density divided by, multiplied by the Z. That is the indication. All right. Now we continue with our derivation. I want to multiply by the Z. That is the indication. All right. Let me just put some few components that I've not put on the diagram. So we have O. All right. Let's put some few components that okay. All right. So this point is what we are calling point A, which is 0, 0, Z, because the only displacement is in the Z axis. So X here is 0. Y is 0, and then Z is actually given by that small z. Now our concentration is on this small triangle that we have here. We have OAP or OPA, whatever way you want to put it. That is where our concern is. So I will not disturb much of this. Just make sure you take note of these small notes that I'm putting here. They will help you a lot when it comes to division. All right. Notes that I'm putting here. Now I want to pick a small triangle, and this triangle is actually what we are calling the. We get this from our figure. Is actually what we are calling the. What we get is that the distance OA is the same as, if we move from O to A, this we can describe it as actually the distance in the Z axis, which is the same as Z, and this is the same as Z magnitude multiplied by the unit vector AZ. Then from there, we can write OP as a vector. This is the distance OP. How can we write it in the y-axis? We know that this is the same as from here to there. It's the same as our R, which we are able to say this is R like that, which is the same as the magnitude of R multiplied by A R in that direction. Or you can say this is A1, so because it is in the y-axis. Now, from the triangle, this triangle OAP mass, what we get is that, okay, so we are saying from triangle OAP, what we get is that OA plus, what we are saying is OA, we are adding OA to AP. This should give us OP. This is simple from the vector analysis. Now, OA plus AP must be equal to OP. This is that. We have already defined what OP is. We have already defined what OA is. What we don't know is actually AP. This is what we don't know. So OA, we have said, is the same as the magnitude of the displacement in the Z direction, which we can call Z as a vector, which is the same as the magnitude of Z multiplied by the unit vector AZ in that direction. Then OP, we have defined it as R, which is the maximum displacement in the Y direction multiplied by the unit vector A1. But what we don't know is this one here, AP. So that means that the implication here is that this we replace with what we have up there. So we have Z, AZ as a unit vector plus AP, which this must be equal to R, AY as a unit vector, which is this one here. So this implies that the displacement or the distance that we don't know for this triangle, which is AP, now should give us, we say, AP must be equal to, so AP must be equal to R, AY minus Z, AZ. like that. So we have defined what this AP is. So we want now to call, this distance. So instead of just calling it AR, we want to use the capital letter R. That's why down there you are able to see that the implication there is that R must be equal to RAY minus Z into AZ, like that. So this is, therefore, what we have is that the magnitude of R must be equal to R squared plus Z squared, all this squared. Okay, so we pick it up from there. R squared plus Z squared, all this squared. Okay, so we next from there, what we have, just a moment. What we have, just a moment. All right. So next, I can wrap this part now, since we are just getting into the mathematics. All right. So next, I can wrap this part now. So the next thing that we want to find this part. So we are saying that that's the electric intensity. So the next thing that is electric field. So density, that's the electric intensity. That is at point P is given by. Right. So what we have is that this is the E, which must be equal to, remember that we have our constant 1/4 pi sine 0 multiplied by the dq over r squared multiplied by a into r squared, which is a unit vector in the r direction. Remember, this r is nothing but the distance from point A to point B in our diagram. Now, what we have is that is nothing but the distance from this r which we have here, this r squared. We know that from definition. This now, it means that it will imply that we write that we have that, which is the E, and we have the Q over 4 pi sine of 0. This we have to multiply it by r squared. Then this must be multiplied by r over r. Of course, this is coming from the fact that this r must be equal to r multiplied by the unit vector, which is the same as r a. We know this. I don't need to repeat that. So this r here is the same as r multiplied by the unit vector, which is the same as r multiplied by the unit vector r. So in other words, this must be capital R. So if we have this AR from here, we know that this implies that AR, which is this one here, if we want to replace it, it's the one that becomes this. So we have AR, which is the same as R over R as magnitude. Now, from there, what we have is that the implication here, it means that this R over R, we can still rewrite it. We know that this implies that AR is the same as R vector over R as a scalar, which is the same as, we know that R is nothing but this RAY multiplied by ZAZ. So this gives us what we have as R multiplied by AY as a unit vector minus Z multiplied by AZ as a unit vector. All this we have to divide by this R. We know that the magnitude of R is nothing but that. So it means that R itself must be equal to R squared plus Z squared, all this about the power 3 over 2. Alright. Of course, this is supposed to be the square of the power over 2 at the moment. Okay. Now we continue on this side. We want now to get the whole lot of this. Where there is R, where there is AR, we have where there is this. Now we need to replace this. Where there is this, which is this, we now need to get this and then put it there. Where there is AR, we have where there is this. Now we need to replace this. Where there is this, which is this, we now need to get this and then put it there. Right. So next, what we get is that this implies that the E, which is the small intensity, as a result of the small dl that we have gotten, this will give us, this is the same as q over 4 pi epsilon 0 into r squared. This must be r to the 3 into r. Then from there we now make replacements of r and that r there. So it means that what we have is that this must be equal to the q, all this multiplied by r a y minus z, then nz, all this divided by 4 pi epsilon 0 into r squared plus z squared into 3 over 2. Remember, this r is r squared plus z squared to the power half. So if we multiply this by r squared, or if we say r to the power 3, this will be equal to r squared plus z squared to the power 3 over 2. That is the reason as to why 3 over 2 is here. Now, we continue to dismantle that and then see how we can reduce that further. So this is the same as you remember very well that we had defined this dq from the beginning. We had defined it as dq is equal to the line charge density into z. So immediately we make that replacement there. Then we are able to see. So what happens is that from here we know that dq, this must be replaced by the line charge density into the z, and then all this must be multiplied by r into ay. Why is this equal to 0? We have remained with that. It's because from the diagram, there is no effect in the z direction. What we are getting is that this component, the component in the z direction gives us 0. If we are looking at the point P, what we are getting is only in the y direction and in the x direction. So the components of the z direction will cancel, and that gives us 0 there. That's why you've seen, even in your notes, the right hand side has indicated that the z axis is equal to the charge present in the negative and in the positive, because you had a line like this, then we had created the y-axis here. This was our origin. If this line goes to infinity, the other side goes to infinity. Remember, this is positive z, this is minus z. So these components are going to cancel. As a result, this whole thing is equal to 0. That's why in the next line you are not able to see this, because it has vanished. And that is very, very important. So you have to take note of that. That's why in the next line you are not able to see this, because it has vanished. Alright? Having said that, then what we have is that this dq has been replaced by that. Z is equal to 0, so we only remain with this r-a-y. Then from there now, we divide this, of course, by our constant, which we explained earlier on. Then this is x squared plus z squared, which is to the power 3 over 2, like that. Now, what we have here is dE, but this is not what we are looking for. What we are looking for is actually the E itself. So in order to get the total E, we need to integrate this side, and we need to integrate on the other side as well, so that we are able to get the total electric field intensity, which we are saying that the the total E must be given by E, which we have already integrated on the left side, should be equal to the integral. Remember that our line, this line, charge, is going to minus infinite to plus infinite. It's just going like that on both directions. And this is where we have to put our y-axis. So we are integrating from minus infinite to positive infinite. So that's why we are able to put this on the integral. This is minus infinite to plus infinite. So write this like that. Then we have the charge density, the line charge density, which is divided by the 4 pi epsilon 0. And then we have r squared plus z squared. All this must multiply by 3 over 2. I mean to the power 3 over 2. So all that we are multiplying it to r z into ay. So let this be our equation 1. Right. Into ay. So let this be our equation 1. Okay. So, after that, then we continue with our derivation. What we see is that in the triangle, of course, in the triangle OAP, what we see is that tan theta, remember this triangle was like this. The triangle AAP, this was our O, this was our P, this is our A. So theta was here. So tan theta from your Socator is easy to actually get some derivation from there. So what we have is that the tan theta, which is tan of this angle here, is equal to z over r. In other words, from here to here, this is what we are calling z, and then from there to there we are calling this r. So tan theta is equal to opposite over what? Over adjacent. That is from your simple mathematics. So we are saying that when z is equal to minus infinite, right? Then theta, which is equal to the tan inverse of z over r, this must be equal to the tan inverse of minus theta minus infinite, which is equal to minus 90 degrees. So this is your point number 1. Point number 2 is that when z is actually on the other side, is plus infinite, then what do we get? We have theta, which is equal to the tan inverse of z over r, which is the same as the tan inverse of plus infinite. This gives us positive 90 degrees. As simple as that. So you have to take note of that seriously. These things you don't need to forget about them. So you remember where you're coming from, you have your triangle, and then from there now you need to make some small, mathematical derivations from here, the so-called Socator, and then you have the tan, which is the opposite of adjacent. Then now you start assuming that z is at the far end, which is minus infinite, and then see what happens to the theta, this angle. And then also you start assuming that z is also at the far end. So what happens to this other angle theta here? So that's what happened. Now, moving on. So what happens to this other angle theta? So that's what happened. Now, moving on. So moving on. So putting these into our equation 1, what we actually get is that the electric field intensity must be equal to, we are moving from minus 90 degrees to plus 90 degrees. Then this is the line charge density multiplied by our constant, which is r squared plus r squared times squared theta. So what we have done is that from our equation, remember very well, this component from our equation 1, it was written as r squared plus z squared, all this multiplied by to the power 3 over 2. Sorry. Now, we know this r is the same as that. Then z, of course, from here, we know that tan theta is equal to z over r. So you can easily say that z is equal to r multiplied by tan theta, as simple as that. Then you get that and replace it where the z is squared. That's how come we've gotten r squared, that squared theta. Because we are avoiding, we want to avoid, either you can eliminate z here or you can eliminate r. So it depends, you choose which one you want to eliminate. From this, you can either write r in terms of z or you can write z in terms of r, which is what we have done here. Then from there you eliminate one component so that you are able to deal with only one. That's right. Alright, so straight away what we get is that this implies that this E must be equal to the integral minus 90 degrees into 90 degrees. All this multiplied by the line charge density over 4 pi epsilon 0, which is our constant. This is cos theta into the theta of A1, like that, which is the same as, this gives us rho L over 2 pi epsilon 0 multiplied by R. All this must be multiplied by A1. So remember that electric field is given in volt per meter. That is the unit. So this is how you find the electric field intensity of an infinite charged line. So therefore E is equal to the line charge density divided by 2 pi epsilon 0 multiplied by R into A1 as a unit vector. So this is how you solve this derivation. So in an example, when I ask you to actually find the electric field intensity due to an infinite line charge, that is the process which you go through. The question may appear just as this, as it is appearing here, and it will not carry any form of diagrams. You have to produce the diagrams yourself, you have to do the derivation yourself. So you have to make sure that you don't mix up these things. Because normally what we see from students from the past is that you ask them about the infinite line charge, they give you the solution for which they've memorized for the charge ring. You give them for the cylinder, they give you for the sphere. So that is the way it is. You don't need to memorize all this stuff, you just need to understand. The moment you see that you are looking at the, for example, like this example that we are just talking about, the moment you see that you are actually dealing with the line charge, what should come into your mind is that you need to immediately produce the diagram. You know that it's an infinite line, so it is going from infinite up to infinite. This is the first thing. This is the charge line. So from there now you decide to create your origin there, which you have your y-axis. This becomes your z-axis. And then from there, you place your pin there. Then you have to cut some dl, which of course is the same as dz in that way. Then you are able now to produce that. You make that your point A, and then from there you can do all these calculations that you're supposed to do. So this is what is very, very important. Produce the diagram first in all the questions of this nature. Then from there now you are able to derive whatever you need from the diagram, and then you are able to come up with the final expression for the electric field density. Right. Whatever you need from the diagram, and then you are able to come up with the final expression. Okay. That having been said, we shall continue. I want us to look at another example. We shall continue. I want us to before we can, it's better we look at one more example before we can call it a day. So we have done the electric field intensity due to a ring. We have done the electric field intensity due to an infinite line charge. Now we want to do another example, which is number 3. So you have to be extra careful on how to resolve all these cases that we are looking at. So you have to be extra careful on how to resolve all these cases that we are looking at. So you have to be extra careful on how to resolve all right, so look at the last example for the day, which is electric field. All right, so look at the last example for the day, density, which is electric field. This is due to density, infinite. This is sheet of charge. Infinite. Remember, we are from looking at a line charge. Now we want to look at a sheet of charge, which is also an infinite. This end is going to infinite, the other side is going to infinite, the other side is going to infinite. In other words, to have, which is also an excited arrangement. So it means that this side is going all the way to infinite, the other side and that, and this other side. So how do we resolve such case? So this is the third example that we have to look at. All right. So we can begin. First of all, like I've said, the moment you are given a question to say find the electric field intensity due to an infinite sheet of charge, the first thing that you need to do is to actually produce a diagram for such an activity. So if you are trying to answer such a question from scratch, you start by dropping equations and all that. It will be very difficult for you to continue because you need to have a diagram that is able to guide you through and to make you get through to your final equation that you are looking for. Right. So first of all, we shall put up the diagram. First, which is what you have there in your notes. So put up a diagram here. We have this as our sheet, which is what you have is an infinite. So put up a diagram sheet of charge. Then of course we can pick that as our origin. We call it 0. Then we have this as our z-axis. We can pick that as our origin. Then, of course, we have this as our y-axis. Then we have that as our x-axis. This is how you begin. You've been given a question, do not panic. Put it into a diagram. After you've put it into a diagram, then you are able to dismantle it slowly but sure, because the diagram is the one that is able to guide you through and you'll be able to actually get to the end. Alright, so what we'll do, since this is a sheet that we are looking at, remember when we were looking at the line chart, we had cut some DL here, which we called descent. Now, in the same manner, we are going to cut a small piece here. We had cut some DL here. So we cut that small piece, which we shall call A. This is our A, which is an area, of course. This one here is DS, which we shall call right. Then we have, it has a charge, dq. Then we have to have a point where we are receiving this charge from. We call that point P. Of course, we'll be using P for all the examples so that you are able to actually not forget about that. So from there now we have the distance from the origin to this point that we've chosen. And then we have the distance from P to A. This is what we are calling A here. This is our point A, of course. Now, what we have is that we actually consider this element, which is the ds. This element we are calling ds, which has a charge dq. And this point, we are considering it to be A. So we have a triangle which is OAP, in other words, or OPA, whatever way you want to put it, but you have to be consistent with what you are doing. Now, here on the surface, we have the surface density. Remember when we were dealing with the line, we have the line charge density. So here we are dealing with the surface. The surface, we are using the surface charge density, which is rho s. You shouldn't forget about that. Now, moving forward, we are using the surface charge density, which is rho s. You shouldn't forget about that. Now, what we get is that we consider, so we are considering. What we get is that we consider an element. This element, which is of course an area, we are calling it ds, which is this area here that we have cut. So we are calling this ds. Of course, then we are calling it from there. Of course, this ds is actually current. So we are calling this charge, which is dq. So this area, a small area, which we are calling ds, is carrying charge dq. Then we now need to sit at a certain point, which is at point P, and then try to find out the charge or the force that we are getting from that point as a result of this point that we have actually cut there. So this means that the surface density, which is rho s, must be equal to the charge density divided by ds. So the implication here is that this dq actually must be equal to the surface density multiplied by the ds. Of course, this ds here, we can easily write it up as, remember, from this to where that ds is, this is r. Then also we have the angle, which is this one here, which we are calling phi. Right, so this we can write it straight away as the surface charge density multiplied by the radius r. This we multiply it by the phi. Of course, this is the phi, then the r. So we have the r here, then we have this which is the phi, which is the angle that we have. So we have the arrow here. Of course, don't forget that this, what we have here is actually cylindrical coordinates. Don't forget that this, what we have here is actually. Now, straight away we are saying electric intensity. Now, straight away we are saying, of course, this is at point P is given by. This is straight away is given by the E must be equal to is given by. Of course, we have the Q over 4 pi, which is a constant, sine of 0 into r squared. This must be multiplied by r in that form. Then, of course, we know that this dq here is nothing but this. So immediately we replace it by what we have there. So we have the surface x into r into the phi into the r. All this we divide it by 4 pi sine 0 into r squared. And then all this will multiply by r. Let that be our equation 1. We'll come back for it. We'll come back and see how we can resolve that. Now, before I can wrap this part, I want to use it so that we are able to resolve. Or I can just take note of this triangle. I'll just pick this triangle here so that, of course, this is 90 degrees. Then you will be able to utilize the rest of the triangle. I'll just pick this triangle here. So, from our diagram, we are able to pick this triangle. Of course, this is our diagram. This is our A, where we have cut a small piece. This is our point P. So, from there now, we are saying from this triangle OAP, what we are able to get is that AO, so AO plus OB, this must be equal to AP. So AO plus OB must be equal to AP, as simple as that. So what we have, the implication here is that, remember very well that this is AO. OA, we say it is R. It means that AO must be what? Must be negative R. Because these are vectors, they have both direction and magnitude. So OA is R from our diagram, so meaning that AO must be the negative of this. So that's why we are writing minus R plus this, of course, is Z. So we have no problem with that. This is Z. This must be equal to R, which we are calling this to be R on the other side. Then from there, the implication here is that minus R of A, which we are calling this of AR, of course. These are actually vectors. Mass plus Z of AZ. Now we are removing the vectors. Must be equal to that way. So, therefore, R must be equal to R squared plus Z squared into square. So, meaning that AR must be equal to R vector over R, which is a scalar, which is equal to minus R multiplied by AR unit vector plus Z into AZ as a unit vector, all this divided by R squared plus Z squared into square. Because this we have defined it there, this we have actually defined it as that. So we are able to make those simple replacements. Right. Moving forward. So we are able to make those simple replacements. Right. Moving forward. Now, remember our equation 1. So the next thing that we need to do now is to make replacements in equation 1. So remember our from equation 1, we need to do now is to make we have in equation 1. So we make replacements. We have dE, which is equal to the surface charge density multiplied by the radius, multiplied by the displacement in the phi direction into the r, all this divided by our constant 4 pi epsilon 0 into r squared. We are multiplying this by r over r. Okay. So that means this implies that this our electric field density becomes the surface charge density multiplied by the radius multiplied by the phi into the r, all this divided by the constant 4 pi epsilon 0 multiplied by r squared. This, of course, we multiply by this r because this one that we have there, of course, this becomes 3 now. This one multiplied by that one gives us that. Then we only remain with the other one on the other side. Now, if we try to multiply further by making replacements, we have the r, which is this one here. Then we have this r, which is also defined as this. So we make replacements immediately. What we get is that this is the surface charge density multiplied by r, divided the r, all this divided by 4 pi epsilon 0. Of course, we have this r is the same as minus r a r as a unit vector plus z into az as a unit vector. Of course, this r becomes r squared plus z squared to the power 3 over 2, like that. So, we have to state something that is very important. So, at point P, what is there is point P is this one here. So, at point P, all the other components, all the AR components, this is R. R is facing in this direction. So this is where we have the AR, like this. All the AR components at point P are going to cancel each other. So we have this AR from this side. If we have, let's say this is our plane. So we have R in this direction. This direction we have minus R. We have R there, then this we have minus R. So these will cancel each other at point P, which is this point up here. So that means that this AR here gives us a 0. So we don't have any components in the AR direction. Right, so we have to mention that. So we don't have at point P components in AR direction. So all AR at point P. So all AR components will actually cancel. So all AR components. So that means we can now have this place here for easy visibility. So that means we can now have this place here for easy visibility. So that means, right? So that having been said, it means that the implication is that the E now must be equal to surface density R into phi. R, all this multiplied by 4 pi epsilon 0. Of course, multiplied by r z squared into 3 over 2. This we are multiplied by z az. So let this be our equation 2. Now, we have this be about 9 by z az. So let this be our equation. So we put here we put r squared plus z squared being equal to, so we put u squared. We put, this means that 2r the r 2r and the r must be equal to 2u du, as simple as that. So the implication is that r and r must be equal to u du. In other words, we are using the substitution method of solving this kind of equations here. We want to eliminate one du. Okay, so having said that, then equation 2 becomes this equations here. We want to eliminate one du. Okay, so having said that, then equation 2 becomes this. All right, so our equation 2 becomes, this becomes dE must be equal to, becomes the surface charge density multiplied by u du into phi, all this divided by 4 pi epsilon 0 into u squared, all this 3 squared. In other words, what we have done here is a technique of substitution method. So we are saying here we actually let. So we want this, all these components here to be equal to u. So we are saying here we actually square like that. So that is what we've done, so that we can make our solution or our derivation so easy. All right. Now, so that we can make our solution or our derivation so easy. From there, what we get is actually this. We have the surface density multiplied by du into the phi, all this. Of course, this u will cancel out of this into 4 pi epsilon 0 into u squared. All this into z of az like that. So now the total is total electric density. So now the total, so this becomes E. Of course, we are integrating now. We integrate this side and we integrate the other side. So if we integrate the E, it becomes E. So E is equal to, so the first integral is where we are moving from phi being equal to 0 into phi being equal to 2 pi. And then the next integral is the one that we have reduced, where u is equal to z into u being equal to infinite of surface density multiplied by the u into the phi. All this we are dividing by 4 pi epsilon 0 into u squared, of course multiplied by z into az as a unit vector. Right. So we continue from there, just find the final expression. Right. So we continue from there, just find the final expression. Right. So this implies that E must be equal to integral of phi being equal to 0 into 2 pi. This implies this is the charge density multiplied by the 5 over 4 pi epsilon 0. Again, we have to multiply that u will be equal to z into infinite of du over u squared into z of az as a unit vector. So, this implies that E must be equal to, of course, the surface charge density is a constant. It comes out, and then we now have that. So this is a constant, that is a constant. So we are just integrating with respect to phi, which is, this becomes over 4 pi sine 0. Here, when we integrate the phi, all we get is phi. Of course, we are moving from 0 to 2 pi. This we are multiplying by, here we are integrating 1 over u squared. So we are just integrating 1 over u squared. When you integrate that, what you get is minus 1 over 4. All this, of course, we have u equals z into infinite. Then we have z, az as a unit vector. So, the implication here is that E must be equal to a surface charge density, of course, which is a constant, divided by another constant, which now gives us 2 pi minus 0. Of course, from here, this is 2 pi minus 0. You don't even need to write it that way. Just multiply it by 2 pi. Then, of course, here when we do the computation, what we get is half. And then we have z into az as a unit vector. So finally, what we get is that the final solution there gives us E, which is equal to the charge density, which is the surface charge density multiplied by 2 epsilon, of course multiplied by az, which is what? The mean. So this is your final solution. When you are given such a question, what I'm expecting to see at the end is this solution here. Alright, so we shall end here for today and we shall continue next week. But before you go, I need to remind you that I'm still waiting for my assignment. I think it's only one who has submitted the assignment. I'm still waiting for the assignment, and then be reminded that the Friday that you'll be in school, the first week that you'll be in school during our time, we'll write test 1. So you have to be studying, you have to be prepared. So we only have 2 weeks in between, I think so. Then the other week you should be preparing to come. So that from there now we can write test 1, then test 2 write, of course, when you are here, as we prepare for the exam. So wish you all the best and make sure that you submit the assignment. I'm preparing the second assignment. Alright? Bye for now. Wish you all the best and make sure that you submit the assignment. I'm preparing the second assignment. Alright? Bye for now. So wish you all the best and make sure that you submit the assignment. I'm preparing the second assignment.